Today I will share with you a method to prove a series which is uniformly convergent on every compact subset of R. Actually, this series is come from Fourier series. And we could use the property and the existent theorem to say it's uniformly convergent. But now I will not use the property of Fourier series. We suppose we don't know these properties. It could also be proved in a natural way. Now let's say it's defined on A, which is a compact set, and A is in minus m to m, and m is greater than 0. If we prove that, we have proved this. Before a very detailed proof process, I'll firstly summarize the main idea of this problem. We know that we want to prove is uniformly convergent on A, and A is a compact set, and A is in this compact set, which is M. If we prove that, we have proved this exercise. And we see, firstly, for pointwise convergence, we use alternating tests to prove this is uniformly convergent. And the main idea is to think of n goes to infinity, and sine 1 plus, actually this period is very large, so it's always increasing. So this term is decreasing and always positive. So we could use this alternating test or say decrease test to prove that. And for the uniform convergence, we expand this into two terms. And one is this, and one is and we step by step to prove they are both uniformly convergent. We use the Weierstrass test for series. We always find a series which is convergent, and to bound this, and then we finish proof. But how to find it? We actually use there's M. We use the compact property here. Since x is continuous on compact set, it must attain its maximum. And since it's defined on this by our assumption, this must be less than or equal to this. Then we have found an upper bound of this absolute value of a series. Then we finish our proof. And then let's begin with the proof of the pointwise convergence. It is an alternating term, and as another way to think of the Dirichlet test. And it needs this term. We should say this is positive, and also this should be decreasing. So how do we guarantee that? Since actually it's not always positive, but we know that if n is bigger enough, actually we could say this is always positive when n is big enough. And then we could say actually this we could write as we could choose n such that we could choose that n since this is a periodic function and this period is actually r pi which is r pi n. And here this is relative to the infinite. So we could draw a picture. We say it's always increasing. If n1 is bigger enough, then we could say it's always decreasing in this if n is greater than or equal to n1, and before n1 it's a finite term, so we could say it's a constant which don't need us to so by the alternating test or Euclid test, it's pointwise convergent. Now let's prove it's actually uniform convergent. Since it's not easy to directly prove it, we could expand this by and we prove that both of them are uniformly convergent, and we finish our proof. Now let's first write this term, which is cosine 1 times sine, and we could move this minus 1 here, and cosine 1 is a constant which does need us to calculate, and we just look at and we want to use test for series to prove it's uniformly convergent. So we want to find an upper bound of it, which is convergent. Now we know that actually for it's always true, and could say is in the neighborhood of it's true. So we could write which is equal to and since x is continuous on a compact side, it attains its maximum. Let's define it on M. And by PE test, this is convergent. So by M test, convergent uniformly. So we have proved this is actually uniformly convergent. Now let's consider this term, which is actually it's not easy, so we need to write it as this form. And we know that actually is convergent by again alternating test or Dirichlet test, since it's always decreasing and is always positive. So it's actually convergent to a constant. So we don't need to care about it. Now let's consider this term. We know that by p-test, since this n is actually convergent. This is convergent since and so by Weierstrass m-test for series, converges uniformly. So we have also proved that actually this term is always uniformly convergent. Therefore, we have proved that this is uniformly convergent.